Okay, this will be a little bit weird because this will be the first lecture, and depending on how this will go, this might be how I lecture you guys just in general. So hopefully I've told you that this lecture is going to be about heating and cooling curves, and I'm just gonna get right into it, okay? So, first we've got here just a little bit of a reminder, right? Yeah, here we go. We've got these concepts, kinetic molecular theory, okay, which again, like I said, this is just a review of stuff from before Unit 2, looking at how do particles behave when they move. How do particles behave when they move? That's what kinetic molecular theory is all about, okay? If we see on this table, we've got some information that's not new. I'm gonna kind of take some notes here. Black. Again, here we've got the states of matter and then what their different properties are. So again, definite volume and shape for solids, definite volume but no definite shape for the liquids, and then for gases, no definite shape, no definite volume. If we take a look down here with the attractive forces, that's something that we discussed a little bit last week. So again, we're talking about those forces of attraction between the particles in a solid versus in a liquid or in a gas. So obviously in a solid, we're gonna have very strong attractive forces. That's why the particles of a solid are tightly packed. And then we're gonna have moderate attractive forces for liquids, and again, that's why liquids are loosely packed. And then, weak forces or no forces at all in the case of a gas, and that's why gases have lots of space within them. So again, just some general ideas of states of matter. They're made up of atoms or molecules, and then what is the behavior of matter because those atoms and molecules move. So again, gases, the atoms and molecules of a gas are in constant motion. So how do they behave? Well, they expand to take the shape of their container because they're in constant motion. So there's a connection between how the particles move and then what does that mean for the states of matter and their properties. Okay, do they keep their shape? Do they keep their volume? All of that is related to movement. Let's see here, I think if I just kind of remove that. Okay, here we go. This slide really just goes over some additional information about the states of matter and their different properties. Nothing that's too important to the conversation we're going to have today, so I'm not going to highlight much of this. Again, this PowerPoint will be up later. You can kind of refer to it later. If you have any questions, don't hesitate. Just come let me know. Some of this information we're not going to worry about at all. Some of it is information you have not yet heard. For example, crystalline or amorphous solids. We never talked about that, so you're not going to worry about that, okay? Okay, now, something that we kind of mentioned, obviously the different states of matter can transform into one another, right? A solid can transform into a liquid when it melts. Let me bring the pen functionality back up. When a solid melts, okay, again, that's the solid going from a liquid, going from a solid to a liquid, we're melting, okay? And then if we continue the process, going from a liquid, evaporation, or the word that, we've been trying to use here, evaporation or boiling, again, that's the process of becoming a gas, okay? So going from a liquid to a gas, we're evaporating or boiling. Before going, obviously we'll talk about this in a second. Obviously, going from a gas to a liquid, okay, that's condensing. We are condensing back together. The particles of a gas are condensing back together to become a liquid, a loosely packed liquid. And then we go from a liquid to a solid when we freeze. Okay, so nothing really new there. I think that information, you probably already knew that information. Just try to keep that in mind. Now, something else I want to kind of say here. Notice melting and freezing. Melting and freezing. They are just opposites of each other, but they are the transformation of a solid to a liquid or a liquid to a solid, okay? So again, those are the same thing, just opposite. I bring that up because, let's just say for the example of, for water, okay? So the melting or freezing is always going to be at 0 degrees Celsius for water, or the boiling / condensing. That only ever happens at 100 degrees Celsius. This is going to be important later on, but again, just to highlight, for water, only water. Different substances have different melting or boiling points, what have you. So I'm just talking about water, just for water. This information, these numbers don't apply to other substances. Water freezes at 0 degrees Celsius and boils at 100. Ethyl alcohol boils at like 77 degrees and then freezes, I forget, but it's way below 0 degrees Celsius. So ethyl alcohol has a different set of numbers. So we're just discussing water. But again, freezing and melting for water always occurs at the same temperature, 0 degrees Celsius. So these things right here, they only happen at 0 degrees Celsius. The evaporation and condensation only happens at 100 degrees Celsius. So again, when we talk about water, again, it melts and freezes at 0 degrees Celsius, okay? So if I asked you, hey, what temperature does ice melt? Ice will melt at 0 degrees Celsius. Or if I said, hey, what temperature will liquid water freeze? Liquid water freezes at 0 degrees Celsius. And it's a very similar case for the condensation and the boiling or evaporation, right? All of that happens at 100. And again, this is just for water, Now, here I put this GIF image in here. This is dry ice sublimating, okay? It is going from a solid to a gaseous state. This is what sublimation looks like. If you've ever seen dry ice, it kind of gives off that fog. We're going from a solid to fog, that solid to gas, that is sublimation. Deposition, the example of deposition that I always give is if you look inside of your freezer, you might notice some ice on the walls of your freezer. That is because water vapor inside your freezer deposited onto the walls of the freezer, and that's deposition. So when we go from a gas to a solid, that is deposition. And like I said, the example that I could think of that you probably see is in the case of your freezer, okay? Yeah, we're making these in time. All right. Okay, heating and cooling curves. Again, heating and cooling curves, which you saw, that's the thing from the Icy Hot Lab. Basically, they help us see how the energy is used all throughout the heating or cooling process, including during a phase change, okay? Like it says here, all phase changes occur at a constant temperature. Therefore, temperature remains constant. Again, when water is melting, if I have some solid water, ice, and it's melting, what temperature does it melt at? It melts at 0 degrees Celsius. So for the entire time that these ice, the solid water is melting, the temperature remains consistent until all of it has melted, and then the temperature goes up, okay? So again, during a phase change, the temperature remains constant. And again, what are phase changes? Melting, freezing, boiling, condensing, all of those are phase changes, and when those things happen, the temperature remains consistent, okay? So, during a phase change, again, going back to the Icy Hot Lab, this third bullet point, I'm just gonna paraphrase it a little bit here, but the Icy Hot Lab remember, what was the energy being used for during the phase change? Well, during the phase change, those flat parts on the graph, the energy is being used to, let's see, what does it say here? To allow the molecules to move apart or come together. So again, during the flat portion of a graph, for example, when water is melting, the solid water is melting into a liquid. So what is the energy being used for at that part? The energy is being used to make the water molecules move apart. So when we are melting, the energy is being used to cause the particles to move apart. When we're boiling, when we're going from a liquid to a gas, same thing. The particles are moving away from each other so that now they can go from being a liquid to being a gas. So that's the energy is being used for. If we're freezing, if the water is going from liquid to solid, the energy is being used now to bring the molecules together, right? Or come together, like it says here. Okay? So again, during a phase change, the energy is being used to make the particles move away or come together. Now, when the temperature is increasing, for that part of the graph where the temperature is increasing, remember, that just means that the particles are moving around more. So a temperature increase means more particle movement, okay? So there's that. Let's see. This information, I'll kind of leave this information. I've kind of gone over a lot of stuff. I kind of want to get to an actual example of what does it look like to make a heating curve, okay? What does that actually look like? So, let's see. Well, just real quick, I've been talking about heating curves. A cooling curve is this right here. Notice how going from left to right, the temperature is going down, right? We're showing that the temperature, we're starting off here. Oh man. We're starting off with our temperature around here. So our temperature is around here. I don't know, this is 75, so maybe the temperature here is 100. Maybe this is the temperature we're starting at. We're at 100, okay? And what happens? The temperature of the gas goes down. What happens here? Here, we are condensing. Here, we're condensing, okay? So we're going from a gas to a liquid. Again, condensing is a phase change. So notice, during the phase change, there's just a flat line. This flat line, it doesn't matter how long the flat line is. Just if there's a phase change, you have to put a flat line. That's the key thing. Now, once the gas is completely condensed into a liquid, at this point right here, where we're all liquid, this is a triangle, okay? Now the temperature goes down, okay? Here, you know. So now the temperature is lowering and it's all liquid. And then guess what happens here at this portion right here? Guess what starts here and ends here? We're melting. We're melting. So again, notice there's a phase change here and there's a phase change here. And guess what? At the phase change, it's flat, okay? Now, the temperatures aren't really important. You know, this substance, you know, what temperature? This substance, it melts at 20. This substance melts. It's melting right here. Okay? This substance is, oh, actually, hold on. Let me take a step back. I'm sorry, not melting, freezing. Sorry about that. Sorry, guys. Equal but opposite. Equal but opposite. We're not melting here, we're freezing. That's actually the bell to let you guys in here, so I'll see you soon. Anyway, Again, this is where we're freezing, and then once the freezing process is done, the temperature continues to lower. Okay, so at this point, we are a solid. We are a solid at this point. Okay, again, real quick, let me get to an example here.